Hello students, let's talk about the Bernoulli's equation. In my opinion, one of the most important equations in the field of fluid dynamics. The Bernoulli's equation is so important, and I told you I lived for a long time in Turkey and I visited Istanbul 30-40 times. It's a great city, and when you go to Istanbul by ship and you drive through the Bosporus by ship, you can see a new museum. It was a former hall for repairing or so, and now it's a new museum. And an artist, Liam Gillick, has written the Bernoulli equation on this big hall, on this museum wall, and you see it really from far away when you come over the Bosporus with a ship. And the Bosporus is a big stream, a big a big channel from the Black Sea to the Marmara Sea, and it's something that has to do with fluid flow, and there's a big fluid flow in this channel, in the Bosporus channel, and that's why Mr. Liam Gillinger took the Bernoulli equation and painted it on the wall. And maybe it looks like as if I've painted it here in the PowerPoint slides. No, it is really a picture of this. So let's have a closer look on the Bernoulli equation. Yeah, that's a derivation of the Bernoulli equation, and I can tell you we have a non-steady solution of the Bernoulli equation, and we can also have a steady solution of the Bernoulli equation, but here's the signs are a bit small. I have also this slide where it is a little bit bigger. And I told you, always when I explain you something from fluid dynamics or from mathematics or any other subject, I also like to introduce a bit the scientists who developed this formula. And here we have our Daniel Bernoulli. He lived from 1700 to 782, and you can see a picture of him, and he did a lot of development in mathematics and fluid dynamics and hydraulics and hydrodynamics, and he also formulated this formula. And this is only one part of the formula, one side, the left hand side, and you have the pressure. Pressure is important. You have dynamic pressure, it's density divided by 2 and velocity squared, and we have also one term of the height, rho g h. Yeah, this is a height difference. So if you have a pipeline system with many height differences, it is important. Or if you have a big lake and a pump system, it is important on which height you pump the water. But sometimes if you don't have big height differences in your pipes, maybe the pressure is more important than you have. Or if you have really high pressure, you can calculate how high your velocity at the exit will be. Okay, and you can formulate this formula also in a balance. So here, this is a formulation of the Bernoulli's equation in a balance. You can have your pressure part, and here the Bernoulli equation is divided by O, by the density. To show you a bit, it tells you something about energy. More or less, the Bernoulli equation is somehow an energy balance. Yeah, you have your specific energy, joules per kilowatt, on the left side. So pressure divided by density is the specific energy, or velocity squared is a specific energy, or gravity constant times height is a constant. And there you have all your values on the entry of the pipe, and here are your values at the exit. And then you can balance. Okay. But of course, we have here in this equation no frictions added, or no temperature changes added. But there are formulations of Bernoulli equation that include these effects. Okay. Here is another picture of a small pipe, and one thing I have to mention, you can use the Bernoulli equation to describe differences at the entry of a pipe. If you compare it with the values at the exit on the pipe, you can make a balance. In this balance, now there are no losses included. Of course, we will have losses. I come to this point later. But what happens if the area changes? If we have here a pipe, like a diffuser with a higher area here and a velocity, and then the diameter changes, you have a higher diameter here, and you have a bigger area, what will probably change? How will the velocity change? If I have a small entry and high velocities, and at the exit of the pipe I have a big exit, your velocity will go down. And so you can formulate this also as a law, as a type of balance. Area multiplied with velocity is equal to area exit multiplied with velocity. You can use this balance also if you want to calculate also like pipe. If you have a big entry and a small exit, what will happen to velocities? Velocity of the water will be higher at the exit. Okay, so an example, already explained. Another example can be this nozzle flow. Nozzle flow means you have a big entry with high fluid flow, and then a small exit, then you get higher velocities. Maybe you know from fireman's pump system and pipe, then you can imagine what I mean. Okay, here's also again it's the same. I like to explain it also a bit in a different way to make a better explanation. Here you have our nozzle on diffuser flow, you have a big area, you have a smaller area, and what happens if in this system, in this nozzle, your pressure will go down. That's also something I tried to explain you in the last lectures when I teach you about weather forecasts. If we have high velocities in a nozzle or a pipe, pressures will go down. If we rise our velocities, pressure will go down. If the velocities get slower and slower, pressure will rise. Okay, so remember, high velocity always means low pressure, low velocity means always high pressure. This can be also explained by Bernoulli's law. If it is a balance and on both sides are same energy amounts inside the fluid, and if we have a high pressure and a low velocity here, we will have on the other side low pressure, then we must get a high velocity. Okay, so that's important laws, keep it in mind. And I think if you try to imagine a pipe system, you can also formulate this area dependency on velocity on your own. Okay, here's another famous guy I want to mention. I mentioned Bernoulli, but I must say Bernoulli was not the only person who invented Bernoulli's equation. That's really often in science that two people in the same time examine same problems, they try to solve these problems, and um, then they get the same solution, and maybe they even do not know about each other, but they come to the same solution. And that's why I also added this picture of Leibniz here. Leibniz lived from 1646 to 1716, and he also did a lot of work in fluid dynamics and in hydraulics, and he also invented Bernoulli's equation, but we don't call it Leibniz equation. But I also want to mention him, and he also worked a lot with computers. Yes, now you say, oh, 16th century, how can he work with computers? But it was totally the same as today. They had problems, they had big fluid flow problems like today, and so they tried to solve them, and so they constructed also computers and calculation machines. Here you see some pictures of this old original Leibniz tabulator, 4-species tabulator, or here's a replica in city of Dresden of Leibniz tabulator, and they used it to calculate fluid flow problems. And you can imagine, if you have a look at these pictures, they look really expensive. Even in former times they had the same problems, they needed expensive computers. And a similar situation is today. Also we need for fluid flow problems really big computers. So weather forecast problems, or testing of nuclear bombs, or development of cars, or development of airplanes, or here development of a power plant, also always have something to do with fluid flow problems. Because how can we build this car? I think it's a Porsche car. How can we build the doors and the mirrors and all the wheels and so and the spoilers? We build it based on calculations of these big computers. Or how can we build big power plants and burners? I think this is a burner of a coal power plant. We design it with computational fluid dynamics, and that's why we need these big computers. And one good example is the high performance computing center in Stuttgart. Yeah, and I think they even have one machine where there's a picture of Leibniz on the machine. Okay, that's why we need them. We need them to solve, let's say, not always the Bernoulli equation. In many cases we solve the Navier-Stokes equations. The Navier-Stokes equations are a development based on the Bernoulli equation. I think that's some kind of explanation. Okay, I want to introduce the Bernoulli equation a bit more. I talked to you about pressures, I talked to you about velocities, and maybe you can imagine the situation when you have an older brother or a younger brother, or you have a husband, and you are in the showers and you want to take a hot shower. And what happens when your friend here enters the bathroom and he pushes the toilet? And what will happen? You will get, if you are in an older house, the water will get hotter. And why gets the water hotter? Because in a normal house, in modern houses, you don't have this effect anymore because you have a ring system. But in older houses, you only had a one pipe system, one pipe with cold water and one pipe with hot water, and both waters, hot water and cold water, are mixed in the armature, and you can shower with it, and you regulate by the water temperature by the armature. But if someone pushes now the cold water toilet, the cold water valve here to fill up the toilet tank, you get a pressure drop in the system, and then the water for the cold water for the shower will be less velocity, less volume flow, less mass flow, and then you have more hot water, and then your feeling is like as if the mixing temperature is much hotter. Okay, that is also one effect of the Bernoulli equation. I took this example from the famous book of Schenger, who is a really famous scientist of fluid dynamics. And Schenger wrote a really good book about all these problems with really nice pictures, and from time to time I take some pictures from his book with the explanations. Okay, that's another picture. I didn't took it from Schenger, but it explains you also what the Bernoulli equation is about. You have here a pipe, and now you have change in the height. So I told you you have a pressure influence in the Bernoulli equation. You have change in the velocity, and you can have change in the area of the pipe, but you can also have a change in the height of the pipe, and this is the part, the term of the equation where you have O times gravity constant times height. Okay, so here again is a consideration of the static pressure, and I repeated a bit. Here again is the Bernoulli equation. You have your part of the velocity, you have your pressure part, you have your part of the height, and you can also have the same terms for the exit. Okay. Okay, here's another picture of a Ramstead streamed on, and on a small ram pressure regarding streamed on bodies. You can, if you have a body like a ball or football or bullet of a rival, and you have a fluid flow, and you get a stream on this ball, then you will always get a pressure here on this body. And now you can also use this Bernoulli equation to get a rough estimation on the ram pressure here on this body. Okay, that's another point where we can use the Bernoulli's law. Okay. Again, here's another picture of the thing I already explained. Again, Bernoulli equation, pressure, static pressure, dynamic pressure, and here again is a height difference. So if you have here your stream tube, you have your entry velocity, exit velocity, and you have a change in the height, ds, you will also get more energy at the exit. And that's another example where we need the pressure formulation of Bernoulli's law, the so-called Prandtl probe, Prandtl tube. Prandtl tube is shown here. It's a small tube, and you have a hole at the entry of the tube, and then you get the run pressure, the higher pressure at the tip of the nose of this tube, and because here's a hole, you can measure how high the pressure is. On the other side, you make a small hole at the side of the tube, and then we don't have a run pressure, we don't have a high pressure, like pressure on the tip, we have only a static pressure. So here at the front we have a combination of static pressure and the velocity influence the dynamic pressure, and here we only have static pressures. So now if we have this Bernoulli tube and we have two different pressures, we can make a small pipe system with some water inside, and by the level of the meniscus of this height of the water, we can now estimate the total pressure, the static pressure, and also the dynamic pressure. And from this static pressure and dynamic pressure difference, you can calculate back to the velocity. So you can use this Bernoulli probe to measure fluid velocities, mainly of air. Maybe you noticed these Bernoulli tubes at the side of an airplane. They're used on airplanes to measure fluid velocity. Here I have a picture. This is an airplane, and here on the side you have this small Bernoulli tubes. There we have a picture of the Bernoulli tubes. You can have even small, bigger ones, and these Bernoulli tubes are used for measurement of the fluid velocity around the airplane. Okay, that's another method to measure fluid velocities by pressure drop. I showed you the Bernoulli tubes, but here I have another method. I have a so-called Venturi tube, and the Venturi tube is mainly based on a similar principle. We don't have a tube, we have a pipe or part of the pipe, and we make the pipe here in the middle a little bit more narrow. Here the pipe is wider, here the pipe is a bit more narrow. In many cases the Venturi tubes are not so they're more rounded, but doesn't matter, it will work also if it's not so rounded. You have this smaller diameter, you have this higher diameter, and now if you remember the law, velocity times area is velocity at the more narrow parts times area here. And so we will have a lower velocity here, higher velocity here, but this will influence our pressure field. If we have low velocities here, we have high static pressure. If we have higher velocities here, we have low pressures here. And so we can make also small holes in this region, connect them with a U pipe, and then if we fill some liquid or quicksilver inside this pipe, in the C pipe, then we can measure the height difference and we can recalculate two pressure differences. And from these pressure differences we can calculate by Bernoulli's law the different fluid velocities. Here's an example, another example of a Venturi nozzle. And Venturi nozzle can also be used to inject something to help mixing. For example, here is a fuel valve for gasoline, and the fuel valve is placed here in the region of the Venturi nozzle, and then if we have an airflow in this channel and we inject gasoline, we have a better mixing. That's where we also use Venturi nozzles. Okay, let's come to the last chapter. Let's come to the so-called Toricelli's equation. And I want to mention Toricelli here. He was also a famous Italian scientist, and he formulated a law that is a bit similar to Bernoulli's law. And if we make the Bernoulli's law, if we delete some parts of Bernoulli's law, we can also get Toricelli's law back. So here we have the Bernoulli flow equation again. We have our static pressure, we have the dynamic pressure, and we have the height difference. And now if we say we have a vessel, and the vessel has a really big area, we have a pressure inside the vessel, and we have a small hole here at the bottom of the vessel. And now what happens if we open here the plug of the small hole and we have a height, then we will get characteristic velocity at the exit here at the hole. And if we calculate now the velocity of the exit based on Bernoulli's law, we can formulate the Toricelli equation. And the Toricelli equation is a square root 2 divided by density, pressure difference, and a term for the height. So here is a more easy version of Toricelli's equation. If we say we don't have a big pressure difference from here to here, don't big air pressure difference, we have here normal atmosphere 1 bar and here normal atmosphere with pressure 1 bar, so we can delete additionally the term for the pressure, and there will be only the term for the height left. So we can formulate that the velocity of the exit is the square root 2 times gravity constant times height of the vessel. So we can use this really easy equation to calculate the velocity here at the exit if we know the height of the vessel. And of course, what happens if the height changes, if the flow of the water is really fast here? What happens? Velocity at the exit will be smaller and smaller. Okay, that's the Toricelli equation. It's the most simple formulation for fluid flow problem. We can also solve this problem with the Bernoulli equation, but if we want to use a more easy equation, we can take Toricelli's flow equation. Okay, so I told you something about Bernoulli equation, about pipe flow, and I want to introduce a bit of friction and a little bit of heat sources, but not too much. I don't want to mention expansion also, but if you have here friction in pipes, if you have friction, you will have losses. If we have the velocity, we have a pressure difference here, we have a kinetic energy change, we have a height change, but if we have friction or temperature rise, we have additional losses. If we want to formulate the balance, we must take this into account. For example, here we have our energy, more or less the Bernoulli. It's also again a Bernoulli equation, and I told you Bernoulli equation is more or less an energy balance. So if we have a system where we heat up, for example a pump that heats up the fluid a bit, that has a bit waste heat, and here's maybe a heating system, then we get some additional heat source, the heat flow, that comes into the fluid, and this will cause also influence on the balance. Okay, so last but not least, I also want to introduce you some special cases that are often used for Bernoulli equations. For example, you can special cases are, for example, elastic containers or artery systems. You can imagine if you have a pipe system that's like the artery system in the body, then you have, or if you have a rubber pipe system, yeah, you can get expansion of the walls. This will influence our or if you have here, for example, a rigid pipe or vibrating flow, we will have special cases. We have an entry by vibration, or we have here, for example, pressure distribution inside the pipe. We will have unusual flow phenomena, or if you, for example, here, like a driving belt, a conveying band, or like a rubber band, then you can have also pressure differences. Okay, let's come to the last slide. Chapter was not so long. Make a small learning control. You should be able to write down Toricelli's equation and also the Bernoulli equation. I think they are so important. You should keep them in mind. You should learn them. You should be able. You should